In this video presentation, we will be looking at the potential applications of polymers in nanomedicine, and in particular in drug delivery. But before we go anywhere, we need to first gain a greater understanding of what a polymer actually is, as well as how one forms. A polymer is a large molecule made up of small units known as monomers. In this case, I have chosen to represent the monomers as men. These are shown on the left. These monomers link together, in this case by the holding of hands, to form a long chain. This is known as a polymer. The process of linking these monomers together is referred to as polymerization. There are two key types of polymerization: chain growth polymerization and step growth polymerization, also known as addition polymerization and condensation polymerization. Chain growth polymerization reactions come in three further types: free radical, cationic, and anionic polymerization. In this video presentation, we will be focusing on chain growth polymerization, and in particular anionic polymerization, because many drug delivery systems rely highly upon this type. In general, a chain growth polymerization reaction goes via three steps: initiation, propagation, and termination. In the initiation step, a species with a reactive end group is formed. This reactive species goes on to attack a monomer in the propagation step, forming the beginning of a polymer chain. The polymer chain continues to lengthen by further reactions of the reactive end group with monomer molecules, until the reactive end group is deactivated. The deactivation of the reactive end group occurs in the termination step. We will now look more closely at anionic polymerization. For anionic polymerization to occur, there are two requirements of the monomer. Firstly, the monomer must be an alkene, and secondly, one of the carbon atoms in the double bond must be bonded to an electron withdrawing group. This is to ensure that there is a slightly positively charged carbon atom in the double bond for the nucleophile to attack. In this case, the nucleophile is an OH- ion. Following attack, a highly reactive anionic species is formed. This anionic species goes on to react with further monomers in the same way that the nucleophile did in the initiation step, lengthening the polymer chain. The property of anionic polymerization that makes it so useful is that there is no termination step. Termination will only occur by reaction of the anionic reactive end group with the solvent, an impurity in the reaction mixture, or by the addition of an electrophile. If the solvent cannot donate H+ ions, and there are no impurities present in the reaction mixture, the polymerization reaction will continue until all the monomers in the reaction mixture have been added to the polymer chain. In control conditions like these, we witness a further type of polymerization, known as living polymerization. Living polymerization has enabled chemists to synthesize polymers more precisely than ever before. In living polymerization, if the initiation reaction is significantly faster than the propagation reaction, then all of the initiators present react with the monomer to form the start of a polymer chain. These polymer chains then propagate uniformly at the same average rate until all of the monomer has been used up. Hence, the polymers obtained have extremely precise molecular weights, as well as very narrow molecular weight distributions, as shown on the graph by the blue line. Living polymerization can be used to achieve a high degree of control over polymer chain architecture. It can be used to synthesize a large range of polymer types, including block copolymers, comb-shaped polymers, multi-armed polymers, ladder polymers, and cyclic polymers. But how does this have any relevance to nanomedicine and drug delivery? Well, it turns out that amphiphilic block copolymers could actually be used in very effective drug delivery systems. Block copolymers are polymers that consist of two different types of monomers organized into two separate sections. In the case of amphiphilic block copolymers, one section possesses hydrophilic properties, water-loving, while the other section possesses hydrophobic properties, water-repelling. The utility of amphiphilic block copolymers for delivery of therapeutic agents arises from this unique chemical composition. In aqueous solutions, amphiphilic block copolymers have a tendency to self-assemble into polymeric micelles. As you can see, the hydrophilic blocks come together to form the shell of the micelle, and the hydrophobic blocks come together to form the core. These core hydrophobic regions are able to serve as reservoirs for a variety of hydrophobic drugs. A hydrophobic drug that many of you may have heard of is paclitaxel, sold under the brand name Taxol. Paclitaxel is a chemotherapy drug that is used to treat many different types of cancer. Currently, paclitaxel is injected directly into the bloodstream, but many have reason to believe that encapsulating the drug in a block copolymer micelle could provide significant advantages. Firstly, encapsulating the paclitaxel in a block copolymer micelle lengthens the time in which the paclitaxel is present in the blood. This is as a result of the stabilizing hydrophilic shell of a polymeric micelle that leads to a lower rate of uptake of the paclitaxel by phagocytes in the blood. Increasing the blood circulation time of a drug is beneficial for drug delivery systems as it increases the likelihood of the drug reaching its therapeutic target. Moreover, the surface of a block copolymer micelle can be modified to enable it to bind to particular receptors overexpressed by tumor cells. For example, the block copolymer micelle PEG-PLA has shown to have potential as a drug delivery system for paclitaxel upon the addition of folate to its surface. The organic molecule folate has the ability to act as a cancer-targeting ligand, as folate receptors are frequently overexpressed by tumor cells. Hence, encapsulating the paclitaxel in the folate PEG-PLA micelle increases the selectivity of paclitaxel towards tumor cells, helping to reduce its impact on healthy cells. Folate PEG-PLA is an excellent example of a block copolymer micelle that achieves receptor-mediated drug delivery. However, there are many more environmentally responsive polymeric drug delivery systems currently being researched, including those that respond to the presence of specific enzymes and antigens, and those that respond to pH and temperature. Enzyme and antigen responsive systems behave in a very similar way to the receptor-mediated systems described earlier. On the other hand, pH and temperature responsive systems rely on the differing physical conditions surrounding tumor cells and healthy cells. Due to the abnormal metabolism and protein regulation of tumor cells, acidic microenvironments form at tumor sites. At these acidic microenvironments, pH-responsive micelles can be changed by chemical bond dissociation, resulting in targeted drug release. Temperature-responsive systems can also be used to deliver drugs to tumors, as the temperature of tumor tissues is slightly higher than that of surrounding normal tissues. From this video presentation, I hope that you have not only gained a greater understanding of the potential applications of polymers in nanomedicine, but also now appreciate how complex micelles are formed from simple monomer units. Thank you for listening.